I have been thinking about how something as simple as counting led us to a whole world of number systems.
It is amazing to imagine early humans just using the fingers or small stones to keep track of things and then one day realizing they needed a better way.
Yes, at first it was all about survival, keeping track of how many animals were in the herd or how many days until the next full moon.
And slowly, as people traded and built villages, counting using fingers or sticks was not enough anymore. They needed symbols, sounds, and marks to represent quantities.
That is when number systems started to form, each culture coming up with its own method. Some used lines or knots, some even carved marks into bones.
Those early marks were the beginning of written numbers, and once numbers could be written, ideas could be shared across time and place.
It all started from a simple need to keep track, then grew into ways of measuring, trading, and later even understanding the world in deep ways.
Without counting, there would be no calendars, no trade, no measurements, not even stories about time or change. Counting is like the root of it all.
Yes, and what feels ordinary today was a huge leap back then, a sign of intelligence, creativity, and community.
I love that it began with something as human as noticing many or few and wanting to make sense of it together.
I have been thinking about something that seems simple but changed everything: the idea of zero.
Zero is fascinating. It is like a quiet partner in the story of numbers, yet it made everything more powerful.
Before zero, people could count and trade, but they could not show nothingness or keep places clear when writing large amounts.
Yes, zero allowed people to understand that having nothing is a real part of the count. It also made it easier to organize digits and write big values.
It is amazing that such an idea took so long to be accepted. Some ancient cultures did not even use it at all.
Then came the realization that zero helped with structure and even helped solve puzzles that were impossible before.
Zero helped shape advanced thinking. It allowed people to calculate, understand change, and build ideas that were deeper than basic counting.
Without zero, we could not have the world we have now. Even basic tools or modern science needed it to exist.
So in a way, zero is not just a number, it is a doorway to understanding the hidden structure of ideas.
Yes, the idea of nothing made everything possible.
I have always found it interesting how Roman numerals look majestic, but feel difficult to use compared to our modern numbers.
I agree, they seem elegant and remind us of ancient stones and statues, but imagine trying to do everyday things like adding long amounts with them.
Yes, even simple writing of larger values becomes a long string of symbols, and there is no real way to show zero, which makes place value very limited.
And that is exactly where modern numbers change the story. With place values and zero, people could handle huge values and do it quickly.
Roman numerals were good for marking kings or carving years on monuments, but they were not built for deep calculation or quick thinking.
Modern numbers made it possible to work with ideas more clearly, to study nature, measure things, and build science itself.
In a sense, Roman numerals were like art, while modern numbers became tools for invention.
That is so true. One set gave us a timeless beauty, and the other gave us a map to explore the unknown.
I was thinking about how we use fractions all the time without even noticing.
Yes, fractions are everywhere, even in daily things like cooking or sharing something equally.
They began when people needed to divide things into equal parts like food or land, and that led to ideas about parts and wholes.
Today they help us understand anything that is not a full amount, from half a glass to a quarter of a journey.
Even more deeply, they form the base of many ideas in music, design, and technology, where balance and proportion matter.
Without fractions, we could not scale things, shrink things, or compare small slices of something big.
They help us work with precision and share things fairly, and even explain ideas like change and movement.
I find it beautiful that a simple idea about sharing can lead to deep understanding of the world.
Yes, from a single slice to complex forms, fractions still remind us how parts create the whole. I have been thinking about how strange it must have seemed when people first tried to use negative numbers.
Yes, it is easy for us to talk about them now, but for a long time people did not accept the idea of less than nothing.
Ancient merchants could not imagine a situation where a number would go below zero, and they thought it was not a real concept.
They often saw numbers only as counts of things you could touch, so negative values felt like a puzzle with no clear meaning.
It took new ways of thinking to accept that numbers could show depths or positions below others, not just amounts of objects.
Once people started seeing numbers as tools for ideas instead of only things, they could count. Negative numbers found their place.
The resistance was understandable because it meant shifting from concrete to abstract thought.
It reminds me how every leap in thinking needs patience, imagination, and a willingness to let go of old ways.
I sometimes forget how powerful the idea of place value really is.
Yes, it is such a simple idea, but it changed everything we do with numbers.
Before place value, people had to use many symbols for big amounts, and it was slow and confusing.
When the position of a digit began to show its worth, maths suddenly became faster and cleaner.
It made writing large amounts easier and helped people move from counting to calculating.
Place value also connected with zero, which let us hold places even when nothing was there.
This helped create patterns and led to ideas that were deeper than just adding or subtracting.
Without place value, we would not have the kind of science or machines we see today. It is part of every code and every measure.
It shows how a simple shift in understanding can open endless paths for human progress. I have been thinking about how early humans measured things long before we had proper units.
It amazes me that people used their own bodies or nearby objects for measurement, like using a hand span or footsits.
That worked well for small communities where everyone knew roughly what those sizes were.
Yes, but it must have caused trouble when someone from far away tried to trade or build something with different habits of measurement.
Exactly, that is how the need for standard units slowly took shape. People needed ways to agree on size, weight, and distance.
Before that, it was all based on trust or comparison. People relied on shared knowledge and memory.
I imagine trading would begin with showing a sack of grain and matching it by eye and feel rather than a scale.
And over time, the need for fairness and clarity pushed people towards fixed measures, just like fixed symbols in writing.
It shows how human curiosity and the need to work together slowly built the systems we now rely on every day. I'm always drawn to patterns. It feels like the world is quietly speaking in repeating shapes and rhythms.
I feel that too, symmetry and patterns seem to comfort the mind like a secret language built into nature.
Even early humans saw patterns in the stars and leaves and in animal tracks, and that curiosity probably shaped their early art and thinking.
Yes. They might not have used the word symmetry, but they knew how to mirror shapes and repeat lines in their drawings and carvings.
That desire to find balance must come from how our eyes and minds work. We notice when something repeats or lines up.
And we find beauty in that. It is like a bridge between what we see and what we feel.
Even modern thinkers study patterns in music and languages and in time itself, as if understanding them brings us closer to knowing the world.
Yes, and symmetry in things like flowers and faces still fascinates us. It feels natural and yet full of mystery.
Patterns and symmetry seem to remind us that beneath chaos there is order just waiting to be noticed. I have always loved how the idea behind the Pythagorean thought feels like a puzzle made for curious minds.
I like thinking of it as a perfect way to understand how the sides of a right corner triangle relate to each other without even seeing the triangle.
It reminds me of arranging 3 square plots of land in such a way that when you place 2 small ones on the shorter edges, the largest one magically matches them on the longest edge.
Yes, and it is like saying if you had 2 small rooms, in one big room, the big one could be exactly the size of the other 2 combined in a special triangle house.
Or imagine building a ladder up a tree starting from 2 points a distance apart and finding the one exact length that fits perfectly to reach the same point.
That image makes it feel like a game of balance and clever guessing. Ancient people must have felt such joy when they discovered this rule holds over and over.
It is no wonder that builders, artists, and thinkers all kept this idea close. It helped them create and explore without ever losing their way.
And even though we learn it in school, it still feels surprising and magical every time it fits just right.
I used to think multiplication was just a fancy way to add the same thing over and over.
I used to think the same way until someone explained that multiplication is more like making groups and seeing how they combine.
That made me look at it differently. When you add, it is like counting one by one. But when you multiply, it is like jumping across a field instead of walking each step.
Yes, and it is even more powerful when you think about things like how many different pairs you could make from 2 groups, or how things grow in layers rather than lines.
It is like planting seeds across rows, then realizing you are not just adding seeds, but filling a whole garden all at once.
Exactly, and that idea lets you see patterns and make predictions you could never reach by just adding slowly.
So multiplication becomes more than a shortcut. It becomes a tool to understand growth, change, and even entire structures.
And once you see it like that, it feels less like repeated work and more like a way to peek into how things really multiply in nature and in thought.
I have been thinking about how algebra feels like learning a new language, one that lets you talk to the unknown.
That is a beautiful way to say it. When we first see those letters standing in place of numbers, it feels mysterious, almost like a riddle.
Yes, and then with time you begin to see that those letters are like characters in a story, each one holding a hidden meaning or a secret value.
And when you put them together with other parts of the sentence, they start to reveal their story. You solve to find out what was hidden.
To me, algebra is like asking a question in a structured way, then letting the rules of the language guide you to the answer.
The more comfortable you get with that language, the more you can express complicated ideas and even dream up new ones.
It gives us a way to speak about things we do not yet know and still follow a clear path to find meaning.
And what begins as a puzzle becomes a powerful voice that can describe shapes, time, change, and even ideas that stretch beyond our sight.
I sometimes like to think of equations as little puzzles waiting to be solved.
That is such a fun way to see them. Each one begins with a question hidden behind symbols and signs.
Yes, and the clues are right there if you know how to read them, like pieces that fit together perfectly once you see the pattern.
I love that moment when you shift one part, move another, and suddenly the whole thing reveals what was behind the mystery.
It feels like unlocking a box, except instead of a key, you use rules and logic to bring balance to both sides.
And every time you solve one puzzle, you get better at seeing how the pieces connect, even when the puzzle looks scary at first.
It also shows how even the most complex ideas can be broken into parts and understood with patience.
Yes, solving equations teaches us to face problems calmly, look for patterns, and trust that the answer is there waiting to be found.
I was thinking about how functions are like bridges between ideas. They show you how one thing changes when another does.
Functions really are like that. They let us describe relationships in a clear and meaningful way.
Yes, and the beauty is that they work like machines. You give them something, they do their job, and then something meaningful comes out.
It is like having a recipe for how one idea connects to another, whether it is time to distance or price to quantity.
Even when the relationship is not simple, functions still allow us to see the shape of the change.
And once you understand that idea, you begin to see functions everywhere in nature and art, and even in the way people behave.
They show us that nothing stands alone, everything responds to something else.
And with that knowledge, we can predict, shape, and understand things that once felt hidden or uncertain.
I find it amazing how graphs turn math from something that felt abstract into something you can see.
Yes, it is like giving numbers a body. Suddenly you see curves, lines, and shapes that say so much without a single word.
It turns equations into pictures and lets your eyes follow how things grow, shrink, or stay steady.
And it helps you feel the flow of change. A rising line feels energetic, a flat line calm and steady.
I love how graphs let us compare things side by side and notice patterns we might never see from just the numbers.
It is like looking at a map. Instead of just reading directions, you feel where things are and how they move.
That sense of direction brings the beauty of math to life, like a story guide pointing the way.
With graphs, the invisible becomes visible and ideas become something you can point to and share in a single clear view.
I used to think polynomials were just long strings of symbols, but now I see them like mountains and valleys waiting to be explored.
That is a lovely thought. I see them like paths that rise and fall, and every route is where the path crosses the ground.
Yes, those roots feel like special places where the whole structure meets balance and quietly says, here I am equal to nothing.
And when you change one part of the expression, the whole curve bends, just like moving one stone under a long rope changes the shape everywhere.
It is as if each part of the polynomial is a voice, and together they form a story that rises and falls across the whole landscape.
And the roots are like resting points, where everything pauses before moving on.
I like how finding roots is like discovering important moments in a journey, moments that tell you something has shifted.
That is why people study them so deeply. Even today, they help us understand change, structure, and balance in a world that is always moving.
It is surprising how something like a quadratic relationship, which seems so abstract at first, appears everywhere in real life.
Yes, we often think of it as just another school lesson, but it is really a powerful way to understand how things move and change.
For example, when you throw a ball into the air, its path always follows that smooth curve shaped by a quadratic equation.
That shape shows how the ball rises, slows, then falls back, and we can predict exactly where and when it hits the ground.
It also shows up in design and building when engineers want to create strong arches or bridges that carry weight in a balanced way.
Even things like car lights or satellite dishes use those curves to focus or spread light in just the right direction.
It is like quadratics give us a way to model any pattern that bends or curves in a fair and predictable arc.
And once you see that they are part of our world, from play to technology, they feel less like puzzles and more like tools we reach for naturally.
I often think about how variables are like flexible placeholders. They let us work through a problem without losing track of what we are searching for.
Yes, they make it possible to ask what if and explore possibilities even before we know their actual values.
It is like having a blank box where you know something belongs, but you can still move ahead with your thinking.
And once everything is in place, you can finally open that box and see what fits inside.
Without variables, we would be stuck with only single examples, not general solutions.
That is what makes them powerful. They let us create patterns and rules instead of solving one thing at a time.
Variables teach us to balance parts of a problem and understand the relationship between them.
They turn uncertainty into possibility and help us turn questions into answers with patience and logic.
I find it interesting how inequalities help us talk about limits and boundaries in a way that feels very real.
Yes, they let us compare things without needing exact matches, like saying this is greater than that or this stays below something else.
It is like drawing invisible fences around ideas, showing what is allowed and what is not.
And that ideas everywhere, from budgets that cannot go over a limit to speed rules that keep us safe on the road.
Even in nature, animals and plants often live within certain ranges of temperature or light, and inequality helps us describe those conditions.
It also helps with fairness, deciding when something is too much or too little and finding a balance.
I like how inequalities show us that not everything must be the exact. Sometimes knowing the bounds is enough to make wise choices.
They remind us that understanding limits is just as important as finding precise answers. Each tells a story about how things can or cannot change.
I often think of logarithms as magical shortcuts. They let us walk through huge calculations without getting lost.
That is a nice way to see them. They take big long steps and turn them into gentle small ones.
Yes, people once spent hours doing repeated steps, but logarithms let them turn those long steps into simple connections.
I imagine ancient thinkers breathing a sigh of relief when they could use tables instead of endless scribbles and checks.
It is like having a clever friend who tells you do not count every grain, just bundle them in a smarter way.
And that clever idea helped explorers, navigators, and scientists work with giant values without feeling overwhelmed.
Logarithms whisper a hidden order behind big things, almost like a secret rhythm that makes everything more manageable.
They remind us that even the biggest problems can become small if we find the right way to look at them.
I always find it wonderful how sequences build patterns that feel both simple and mysterious.
Yes, especially the famous sequence that starts with one, then another one, and each new value is the sum of the two before it.
That pattern feels like a gentle unfolding, and it shows up in places we never expect.
It is living inside flowers, shells, and even the way plants grow their leaves.
The magic is how something so small and simple can grow into a grand pattern that nature seems to adore.
And even in art and music, that same pattern gives balance and beauty. It feels almost universal.
I love how the more you explore it, the more connected it becomes to life and design.
It reminds us that hidden in everyday things are deep patterns waiting to be noticed and celebrated.
I have always noticed how geometry gives shape to the buildings we see around us and even the patterns in art.
Yes, every structure seems to borrow from the language of shapes and lines, whether it is a simple hut or a grand cathedral.
Architects use angles and curves that fit together perfectly, and geometry helps them make sure things are beautiful and strong.
And artists do the same. They create balance through symmetry or surprise us with irregular forms that still feel just right.
When I look at a bridge or a temple, I see triangles, arches, and circles working together like a grand composition.
It is powerful because it connects logic with emotion. Geometry makes structures stand, and shapes make them sing.
Even in modern designs with glass and steel, the same rules apply. Every line has a purpose, and every angle tells a story.
And what began as simple drawings in the sand grew into the foundation for everything from tiny ornaments to towering wonders.
I often think about how angles and triangles are like the quiet heroes of shapes. They appear in everything but do not always get the praise they deserve.
That is true. Triangles are the most stable shape, and angles are what let us measure and understand how things connect.
Yes, whenever you see a building or a bridge, it is full of triangles hidden inside, keeping it steady and balanced.
Even in nature, trees, branches, and mountains hold their strength because angles distribute forces in smart ways.
And without angles, we would never know how to draw maps or guide ships across oceans or understand light and shadows.
I like how something so simple quietly supports the world we live in and helps us explore what lies beyond.
Triangles with their three sides prove that you do not need many parts to create something strong and meaningful.
And angles let us see how things lean, turn, and meet. They make sense of space and shape in a way nothing else can.
I find it fascinating how Euclidean geometry feels like the world we know, with straight lines, flat surfaces, and familiar shapes.
Yes, it is the kind of geometry we grow up with, and it matches what we see every day on a piece of paper or a calm field.
But then there is non-Euclidean geometry, which feels like stepping into a dream world where lines bend and space curves in surprising ways.
It is like imagining that if you walked straight long enough you might return to where you started, or that the angles of a triangle might not add up the way we expect.
That idea opened doors for thinkers to understand the shape of the entire universe, not just simple shapes and rooms.
And it helped scientists explain how space can bend under the weight of stars and planets, which was once only a bold idea.
Euclidean geometry feels like home, and non-Euclidean geometry feels like adventure, yet both help us describe and understand different realities.
They show us that there is more than one way to measure and observe the world. It all depends on where we stand and how far we look.
I often think about how trigonometry stretches all the way from ancient stargazers to modern city builders.
Yes, it began with people looking up, trying to measure distance and height using just angles and clever thinking.
Those early sky watchers used trigonometry to track the movement of stars, measure the Earth, and even predict celestial events.
And that same knowledge now helps engineers build skyscrapers, bridges, and tunnels with perfect precision.
It is like a thread connecting ancient observatories with the skylines of today, all through the language of angles.
I love how a small handheld tool once measured the distance to the horizon, and now computers use the same ideas to shape our cities.
Trigonometry gives us the power to reach high and dig deep, guiding us with invisible lines drawn between known and unknown points.
It is wonderful how something as simple as a triangle still defines our tallest dreams and deepest discoveries.
I always feel that geometry and movement are deeply connected, as if shapes and paths are just the language of how things move.
That makes a lot of sense. Everything that moves follows a path, and that path has shaped distance and direction.
Yes, even when we drop something and watch it fall, we can see a curve forming a gentle arc that geometry helps us describe.
And in physics we learn that the world is full of hidden patterns. Objects move in precise ways that can be drawn with lines and curves.
I like thinking of geometry as the canvas and physics as the paint. The laws of movement will always follow that canvas.
Even when things twist, turn, or spin, geometry shows us how each motion fits together without confusion.
It is why we can predict how planets move or how a ball bounces, because every motion carries a geometric truth.
And that connection turns the physical world into a great dance, where each step can be measured and felt through shapes and space.
I have always been curious how prime numbers end up being the guardians of our online privacy. I mean, they are just numbers, right? How do they lock and unlock secrets?
It is poetic if you think about it.
These simple numbers, indivisible in nature, hold the key to protecting everything we do on the internet.
Cryptography relies on the idea that, while it is easy to multiply two prime numbers, it is incredibly hard to reverse the process and find those primes from the result.
That is the foundation of RSA encryption, right? You pick two large primes, multiply them, then use that product as part of a public key. Everyone can see it, but no one can break it unless they factor it.
Exactly.
And factoring is the heart of the security. If someone could efficiently factor large numbers, the whole system collapses. That is why the search for faster algorithms scares cryptographers. They are always looking over their shoulders.
So every time I send a message or log in somewhere, prime numbers are behind the scenes.
Yes, working quietly, protecting you. Even digital signatures and secure websites depend on them. Every green lock symbol in your browser hints at centuries of number theory.
It is wild. We use this every day and never think of the math. Makes me wonder what happens if someone finds a clever way to factor large numbers.
Then the entire internet changes overnight.
We would need new systems, maybe based on quantum-assistant algorithms.
The irony is that cryptography is both brittle and beautiful, sitting on the shoulders of mysterious primes.
Math, once again, shaping our world invisibly. It is not just about counting anymore. It is the shield around our secrets.
And until someone cracks that shield, the primes keep watch, silently and elegantly.
You know, whenever I hear the word optimization, I picture giant warehouses and trucks lined up in perfect formation, all moving in sync. It feels almost like a machine breathing.
That is a beautiful image. And in a lot of ways, it is true. Supply chains are like living systems, constantly adapting, constantly needing to be efficient. Optimization is the math that keeps them alive.
It fascinates me that something as abstract as linear programming dictates if your package arrives on time or if a store runs out of stock.
Absolutely.
Think about a company shipping products worldwide. They need to decide which warehouse to ship from, how many trucks to use, the best route to avoid congestion. All of that is an optimization problem wrapped in real-world constraints.
And I guess time is the ultimate constraint. Minimize time, minimize cost, maximize output. Sounds like a puzzle.
A puzzle with huge consequences.
During the pandemic, when supply chains broke down, it became obvious how delicate that puzzle is. One missing piece, and suddenly there is no toilet paper anywhere.
So the math behind it is not just academic. It is what keeps economies running.
Exactly.
Algorithms decide inventory levels, reorder points, even where to build new factories. And new technologies like machine learning are making predictions even more accurate.
That is brilliant. The better the math, the smoother the flow of goods. Optimization is like the hidden conductor of global trade.
Yes, silently tuning every movement. It is a strange kind of elegance.
Numbers flowing across spreadsheets, matching the flow of trucks across borders.
Next time I get a delivery early, I should thank an algorithm.
And thank the mathematicians and engineers who made sure the world keeps moving in the right direction, even when it seems chaotic.
I always hear people use probability and statistics like they are the same thing. But they are not, right?
Not at all. They are related, but they approach uncertainty from opposite directions. Probability starts with known rules and predicts what might happen.
Statistics starts with what has already happened and tries to infer the rules.
So, probability is like saying, if I roll a fair die, the chance of getting a 6 is 1 in 6. That is based on known assumptions.
Exactly.
You know the structure. Statistics comes in when you do not know if the die is fair. You roll it 100 times and observe how many 6s appear. Then you use statistics to estimate if it is fair or loaded.
So one predicts forward, and the other works backward.
That is a great way to put it. Probability asks, given a model, how likely is an outcome? And statistics asks, given observed outcomes, what is the most likely model?
There is a nice symmetry there. But I bet that is where people get confused.
Yes, especially when the same tools appear in both. For instance, both use concepts like distributions, but for different purposes. Probability uses them to describe randomness. Statistics uses them to draw conclusions from data.
That makes me think of weather forecasting. Meteorologists use past data, that is statistics, but also simulate the future, which uses probability.
Perfect example. It is like two sides of a coin. One learns from the past. The other predicts the future. Together, they make sense of uncertainty.
That gives me a new respect for how these fields work together. They are different languages that describe the same mystery, randomness.
Yes, and knowing which one you are using helps you ask the right questions. Ask probability when you have the rules. Ask statistics when you have the results and want to uncover the rules.
I was listening to some music files and noticed how small they can be. I heard something called Fourier series is involved. How does that work?
It is fascinating. Fourier series is a way to break down any signal, like a sound wave, into simple repeating waves. Think of it like taking a complex melody and finding the basic notes that build it.
So even the most complicated sound can be seen as a combination of simpler waves?
Exactly.
Each wave has a certain frequency and amplitude.
When you add them all together, you get the original sound.
This is what Fourier figured out, that any periodic signal can be represented as a sum of simple waves.
That explains the math part. But how does it help compress audio?
Once you have the wave breakdown, you can see which components are really important to what we hear.
Less noticeable parts can be reduced or removed.
That makes the file smaller without a huge loss in quality.
So it is like keeping the main ingredients of a recipe and leaving out tiny spices we might not even taste.
Perfect analogy. The ear is forgiving, so compression can trim the less audible parts. That is how MP3s and other formats shrink audio efficiently.
I always thought audio compression was magic. Turns out it is pure math at work, slicing sound into waves.
Yes, Fourier's series quietly transforms noise into order, letting us carry music in our pockets without losing its soul.
Quantum computing always sounds like science fiction. How can math make something so strange even possible?
It does sound strange, but math is the backbone. Classical computers work with zeros and ones, but quantum computers use qubits, which can exist in multiple states at once. Math helps us describe and manipulate those states precisely.
So qubits are not just on or off. They can be both?
Yes, in a sense.
They can be in a combination of states, which is called superposition.
Linear algebra in complex numbers let us model these combinations and predict how they behave when we manipulate them.
That sounds abstract. But I guess without math, we could not control or predict them.
Exactly.
And there's another concept called entanglement, where qubits are linked.
Math tells us how one qubit's state affects another, even across distance.
That is crucial for quantum algorithms.
And these algorithms are what give quantum computers their power.
Yes.
They solve problems that would take classical computers an impossible amount of time. Math designs the algorithms, analyzes the outcomes, and ensures the results make sense.
So quantum computing is like math brought to life in the tiniest particles.
Beautifully said. Without the precise language of math, qubits would just be mysterious flickers. Math gives them structure and lets us harness their potential.
It makes me appreciate how ancient concepts like linear algebra are now shaping the future.
Absolutely.
Quantum computing is proof that math is timeless, quietly guiding both the smallest particles and the largest innovations.
Sometimes I wonder what math will look like in the future. Will we reach a point where everything is solved, or will there always be mysteries?
I think there will always be mysteries.
Every time we answer one question, new ones appear.
Mathematics grows with human curiosity. The more we know, the more we realize how much we do not.
That is humbling. So the future of math is tied to the growth of human imagination itself.
Exactly. We are not just discovering truths, we are inventing new ways to see the world.
New branches may emerge that we cannot even imagine today.
And with technology evolving, like artificial intelligence, we might explore patterns and connections that were invisible before.
Yes. AI might help us test ideas faster, find unexpected links, and even suggest new directions.
But human intuition and creativity will still be central.
So math will become more collaborative, blending human insight with computational power.
That is right. And beyond formulas, it will help us understand complexity in nature, society, and even consciousness. The frontier of math is limitless.
It makes me excited to think that every generation of thinkers adds a new layer to this ever-growing structure.
And that is the beauty of mathematics. It is not static. It evolves, reflects our curiosity, and forever stretches our understanding of what is possible.